I want to first thank Morgan for the introduction, for the kind introduction, and for inviting me here. It's always great to be back in Harvard. And today I'm going to talk about our recent work on diffusion models. I guess the nice thing about speaking first is that the quality of the talks will only go up after that. Okay, so since this is a workshop on mathematical foundations for AI, in this plot, I just show you several significant events in the AI evolutions. As we all know that AI we have seen AI has experienced meteoric growth in recent years. And roughly speaking, we can sort of categorize AI development in this three stage, where you see statistical learning stage and several significant events like the development of SVM, random forest, the lasso estimator. And then we see the deep learning revolution. And then more recently, there has been a huge trend on LLMs and the foundational models. And among many other features, there's a clear trend for AI models from being more discriminative, where the goal is to do classification or to do the prediction upon seeing new samples, to be more generative. Okay, so in this generative AI era, diffusion models actually hold tremendous promises. Firstly, it was developed for high-quality image synthesis and generation, and then it has been used in various different domains, such as protein structure generation, offering new tools to design drugs and medical molecules. And then it has been used for reinforcement learning to model complicated policy and generation of plausible reinforcement learning trajectories. And then it has been used in multiple different domains, scientific domains such as weather forecasting, medical imaging, and material sciences, and among many others. Okay, so in this 2 and 3 years, people started to think about why diffusion models work so well in practice, and start to develop a theoretical understanding of diffusion models. Here, I only list a very, very incomplete, give you a very incomplete literature review. All of these papers sort of appear in this 2 and 3 years, and this has been obviously a growing, very, very growing and promising field. So the generative models, in a nutshell, it means that you're giving a bunch of training data, for example, x1 to xn, generated from some distribution p data. And the goal is to generate new data sample or new data instance that looks similar in distribution to the training data. And of course, a natural approach from classical statistics, is to do density estimation, where you have this bunch of training data. You will use your favorite tools, classical statistic tools, to learn this density first, and then generate directly from the density you learned. Right. So an obvious approach is to model this distribution from a class of functions parameterized by theta, where we can write the density function as e to the minus f theta divided by some normalizing constant. Right. That is what people normally do. And then after that, we can use our favorite maximal likelihood or maximal posterior to estimate our theta, and then that speaks out our the density. However, in practice, this is often intractable because we need to learn this normalizing constant z of theta. So either you need to restrict yourself to a parameterization class so that the z of theta can be easily learned or modeled, or we need to spend more computational resources to learn this normalization constant by running extra MCMC, for example, right? So that's why it's often intractable. So another approach is to go through a score function. The score function is defined as you take the log of the density and take the gradient of that. You can imagine that if you do the same thing and model the density using the parameterization that we talked about, f of theta, then once you took the gradient of the log, then the normalizing constant goes away. So it's pretty nice. You don't need to compute this z of theta anymore. So here on the right, I plot the score function, the vector field, and the density for two mixture of Gaussians. Okay, so you can see that the score functions, they point towards the higher probability density area. So they does give you information about the true density. Okay, so now we know that modeling the score function is sort of nice. You get rid of the annoying normalization constant. So what do diffusion models do? Well, diffusion models in a nutshell contain two stochastic processes. One forward process where you have your true distribution. You gradually add noise to the distribution and perturb the data until it looks like just a white pure noise, white noise, right? And that's the forward process. Usually people think about that using like a OU process where you directly, at each step, you add just Gaussian noise, pure noise to your data and diffuse the data into white noise. And what is tricky is the reverse process where you want to start from a pure Gaussian and revert this process and back and gradually generate a distribution of data that hopefully of the same distribution as your training data. So that's the reverse process. So the reverse process is more tricky. So it turns out that if you know the score function, then this is actually easy. Once you know the score function, in the classical literature of SDE, there exists a reverse SDE and a reverse ODE, where the drift term only depends on the score function. And once you have access to that, you can generate samples by reversing the SDE. Okay, so the question is, in practice, we don't have access to this score function, right? So now, starting from the seminal work by Sitan and Xing-Ho et al. And co-authors, now it becomes a very standard approach to sort of divide this whole task into two phases. The first phase is to do score learning or score matching, where you can use your favorite structure, neural network or different structures to learn the score function. And the second phase is once you have access to the estimate of the score function, you can generate samples using those score functions. Okay, so these are divided into these two phases. So let's first talk about the first phase, about the score matching or score learning. The score matching, your target is the gradient of a log density function. And in view of the classical treatise formula, this can be written as a denoising problem, where the true score can be written as this conditional expectation. So given the linear combination, that's your observation of this your data with some noise, some Gaussian equal to some x, you want to find this conditional expectation. So this is a purely denoising problem. So there has been different ways of doing of estimating the score. For example, you can use a non-parametric methods such as kernel method to do score estimation, or you can use AMP, approximate message passing, for score estimation. That's what this Wei and Montanari paper does. And or you can try to analyze the performances of different structures of neural networks. Okay, so people have done this. This has also been a growing literature on this topic. Okay, now suppose that you are given this score estimates, and now you want to do sampling. So the two mainstream sampling approaches are one, DDPM, the denoising diffusion probability models. This now becomes a really, really popular, highly cited paper. And the other is more, is called the denoising diffusion implicit models. So the difference between these two is that the first one is a stochastic sampler. The second is a deterministic sampler. I think many of you probably have heard of this. So just to maybe give you like a short recap, the DDPM, the stochastic sampler, works as follows. So you start from, this is the forward process, okay? So you gradually add noise to diffuse your data. So the stochastic sampler start from a pure classic standard Gaussian, and it's an iterative procedure. You start from a Y capital T and move backwards. At each time, you set YT minus 1 to be just a deterministic function of the YT and the score estimate at YT. Okay, and you add independent standard Gaussian to that. Is that clear? So this is the procedure. It's an iterative procedure starting from pure Gaussian. So this is the standard approach of the DDPM. It has been used. It's now has been used everywhere. And the deterministic approach is even simpler. You start from a standard Gaussian noise, and you iterate backwards. At each time, YT minus 1, you set it as a deterministic function where you have this YT, a linear combination of YT and the score function. Okay, you don't, yes?
Can I just ask, maybe it's a stupid question. So is it obvious that the right place to evaluate the score function is YT and not some slight like interpolation or deformation of YT and the other Y?
Yeah, that's a great question. Actually, people have proposed different ways to for this score estimates. And it turns out that if you are allowed to evaluate the score at multiple different places, then actually this DDPM and DDIM, they can be accelerated just because that you can sort of discretize your SDU ODE differently so that you can get a higher order approximation of this SDU or ODE to accelerate these samplers. Yes, as we will talk about that later, these two approaches where you evaluate ST and YT are the most natural kind of choices.
Thank you.
Yeah, sure. Please feel free to stop me if you have any questions. Okay, so these are just several introductions to these two popular use samplers. Before going to our main results, let me first try to prepare you with the prior convergence theory that we know about these two samplers. First, I will talk about the DDIM, the deterministic sampler. Well, under mild assumptions on the target distribution, this P of data, in this earlier work of us, we are able to prove that the DDIM sampler, remember this is a deterministic sampler where you're given a Y capital T, it forms a deterministic trajectory for the generation of Y0, and that you use this as your final sampler. And we characterize the TV distance between your target, the distribution of X1 and the sampler Y1. And it's actually controlled by three terms. Let me explain. Let me just unpack this for you. If you ignore the second and the third term, and if you want to find distribution such that the TV distance to your target distribution is smaller or equal to epsilon, the number of iteration that it requires will be d over epsilon. This is just by setting the first term to be smaller or equal to epsilon. And you solve for the capital T, that's the number of steps you take for the diffusion models. So it turns out that you have d over epsilon number of iterations, meaning that that's the number of steps you need to take in order to generate either a great image or reconstruct a protein structure. Is that clear?
So
yes.
D was the dimension. And
D, yes, yeah. D is the ambient dimension of the distribution. So you aim, yes.
So mentions assumptions. It's one of them that you need the target distribution to be lower bounded. But then
Very good point. So let me unpack the assumptions for you. So the first assumption is to put the assumption that we will put on the target distribution, where we assume that the support of my target distribution with probability 1 is bounded by this by a large constant that can scale with t. Okay, so compared to prior literature on diffusion models or on sampling in general, this is very mild. We don't need assumptions on like a log concavity or smoothness of the distribution. Okay, because we allow t to grow very large. So this is like a kind of a mild assumption on this distribution. Okay. And the second assumptions that we want to make, which relates to the third and the second and the third terms, is about the quality of your score estimation. So the quality of the score estimation, we assume the following two. We assume on average, if you average across time, the expectation of your the L2 error of your score estimates needs to be bounded by this epsilon score. And the Jacobian of your score estimate needs to be bounded on average. These are all in terms of the average across iteration needs to be bounded by epsilon Jacobian. Okay, it turns out that the first assumption is quite mild compared to the literature, because in the literature, people have to assume the L infinity norm of this score estimate. Here, we only require expectation and average over time. And the Jacobian estimation error is needed for deterministic sampler. Remember, we have stochastic sampler and deterministic sampler. This is required for the deterministic sampler. And counter example exists.
Is your norm?
Oh, this is the operator norm. Yes. Yeah. Okay, so under this two, can recap. So our TV distance control is robust with respect to the score estimation error. Okay, so it allows some error in your score estimate. And another remark is about the D dependence. So previously, when people analyze the samplers, usually there's like a large dependence on the power of D, where we are able to get a sharp dependence on D using tools in stochastic localization. Okay, so having this linear dependence in D is actually very non-trivial. That's for the DDIM, the deterministic sampler. In terms of the DDPM, the stochastic sampler, this D over T scaling is developed in this paper. This it's a paper after ours for TV, and Benton et al. They have developed the same scaling, but for a KL divergence, different metric. Okay, any questions so far? So that's the prior theory. So you know that the iteration complexity is of order D over epsilon if you're aiming for epsilon accuracy.
So can I ask, like, this sort of suggests that the stochastic sampler from this point of view is like just has better set of sample complexity. But is the point that it's like harder to than actually estimate well the score for the stochastic one?
Well, you see that this have the same scaling for
You don't have
both.
the other two terms, you're saying.
You don't. Oh, sorry. Yes, you do have the same terms there. You don't need a Jacobian for the stochastic, but yes, but compared to the DDPM, actually DDPM, it's much harder to analyze than the stochastic version, just because adding noise kind of smooth things out. Usually the case it will be. Okay. Yes.
So for DDIM, we have some control also on the norm of the great control. Yeah. For DDPM, should we also have something like this? Because otherwise, if the distribution is discrete,
Oh, okay.
we cannot, we need some.
Yes. So here, I'm talking about continuous distributions where you have like a density function. However, in the discrete case, people have different parallel kind of framework where you also can develop things like that. Yes. Point. Other questions? Okay. So that's the prior result that is known. So that we are like kind of prepared to know what's our expectation. And this talk, I want to mainly focus on the adaptation of diffusions to low dimensionality. Okay, so we know that d over epsilon is what you should expect in general. Actually, there are actually lower bounds showing that this is the iteration complexity you can hope for. But in practice, these two samplers actually they generate very good samples, even in hundreds or tens of steps. So we want to know if d over epsilon is something that you can do at best. Well, so if you think about the benchmark data set, such as ImageNet, so in ImageNet data set, the dimension of the image for each one of them, you have hundreds of thousands of pixels to model each image. And N is like 14 million plus images in this data set. This is now a classical benchmark data set in computer vision. And people start to think about maybe there's some structure in the image data that we're looking at. In fact, when you go and estimate the intrinsic dimension of ImageNet, it turns out that the intrinsic dimension is 43 for ImageNet. Although this is a huge dimensional data, it's hundreds of thousands of dimension. So if we d over epsilon is still something that you're looking at, then it becomes really large, right? Because d is 100,000, and the question is that because the data is intrinsically lower dimension, so that we can hope that DDPM converges faster. So that's something we want to look into. The question is, can diffusion models, without changing the algorithm itself, adapt to low dimensional distributions if your distribution is actually low dimensional? Okay, so now let me recap what, let me introduce what do I mean by intrinsic dimension. Here we, for intrinsic dimension, we say target distribution is of dimension k if the log covering number of the support of the distribution is scales with k instead of d. So in general, you should this should scales with d simply because you're dealing with a d-dimensional distribution. And in the cases where it actually scales with k is, for example, if you have a k-dimensional linear space in the sense that your target distribution is actually supported on this linear space, then this log covering number scales with k. And also if you have like the support, which is k-dimensional manifolds, also scales with k, etc. Okay, so this is like a standard way to measure the intrinsic dimension of some distribution. Okay, is that clear? Okay. So then for distributions that actually has k as its intrinsic dimension, we're able to prove that the iteration complexity scales with k instead of d. So instead of d epsilon, it scales with k epsilon. But here, notice that we changed the metric. It's the KL divergence instead of TV now. Okay. So
what happens if k is 0? If you have a discrete distribution?
Well, so here we only consider continuous distributions, but when k, yeah, so when k is very, very small, then it's like it should scale with 1 over epsilon, for example, instead of d over epsilon.
Continuous in what sense? Like they're now supported on these like, low dimensional.
Yeah,
So
yeah.
continuous along the support.
Right.
Okay.
Yes, continuous along. Yes. Yeah.
So what's the intuition then for why this is working? Is it because you're using something powerful to learn the score and it's doing some kind of?
Yes, very good point. I will answer your question after I sort of give you some implications of this result. Yes. Just other questions? Okay, so let me just briefly comment on this comparisons and implications. So to compare with the previous work, we get an optimal dependence on K. And also after our work, there's another nice paper where they develop K over epsilon complexity in terms of the TV distance. So here we have the KL. Okay, so let me give you some intuition why DDPM can adapt to this lower dimensional structure. Okay, so just a remark that we do not change the algorithm itself. So the DDPM is still in the original design. So we do not change DDPM in order to adapt this low dimensional structure. You just run DDPM as this is a full dimensional distribution, and then, but the DDPM, it turns out DDPM adapts very well to those distributions. Okay. Yes.
So then in the assumptions, you're still assuming you can learn the score just as well. So it's plausible. It's harder to learn the score when you have a.
Yes. So now yes. So the error of the or the quality of your sampler still have two parts. One part you have the more like an optimization error or iterate that associated with the iteration complexity. The other is score estimation error, where of course when you have a low dimensional distribution, you need to develop your score estimate so that that part adapts to the low dimensional as well. Yes. Yeah. So the reason why DDPM can Right. Yeah. So for this result, we don't need to know the intrinsic dimension, the K, because you still run DDPM, but DDPM automatically adapts. So basically, if you have the ImageNet, the iteration complexity is of order 43 by epsilon instead of hundreds of thousands by epsilon. It means that you only take you like hundreds or tens of iterations in order for DDPM to converge. However, you still need a good score estimate in the sense that you want to find a score estimate such that the estimation error also scales with K. In that part, you actually need to estimate the intrinsic dimension. Yes. Other questions? Okay, let me give you some brief intuition why DDPM is actually can actually automatically adapt to the low dimensional structure. Recall that we have the backward SDE. If you do not have error in your score estimate, then the backward SDE. Okay, so the backward SDE has a score function inside. and recall the treatise formula, you can always write the score function as the conditional expectation and the linear combination of conditional expectation and your YT. You plug that in, then the backward SD can be written in this way. In fact, now you have a term that is linear, the drift term, that has one part that is linear in terms of YT, and the one part that depends on the conditional expectation. So this conditional expectation is conditioned on your XT. You want to find the expectation of X0. Okay, so now you have a SDE, looks like this. And then what you should expect is that you can find the function ft, which is of this form. And then this function can be written as, this SDE can be discretized by invoking this function inside so that the drift term only depends on the conditional expectation. So in the sense that you directly integrate this YT out, work with the linear parts, and then you only discretize the conditional expectation so that the drift term only depends on the conditional expectation. And the conditional expectation is actually very, very nice if you think about a low dimensional X0. So in the sense that this conditional expectation will also have a low dimensional structure. So that if your drift term only have a low dimensional structure, you can imagine your DDPM sort of adapt. If the DDPM is one such discretization, then you can imagine that DDPM should automatically adapt just because the drift term has a low dimensional structure. Does that make sense? On a high level? So in fact, DDPM, although originally it was proposed by computer scientists, where they try to maximize the variation of lower bounds to derive DDPM. But it turns out that DDPM can be understood as a different way of discretizing your stochastic process so that it actually adapts to the low dimensional structure if you have any for a target distribution. Does that make sense? So meaning that although it's not proposed for this reason, but it can be understood as a different discretization of a stochastic process. And that discretization is actually really nice so that it can automatically adapt to low dimensional structure. Clear? Questions? Yes.
It's like how the intrinsic dimension K comes in. So is this comes in because of something like the union bound over all the covering scales or covering balls? Or
Yeah. So the low dimensional structure comes in to analyze this conditional expectation. More specifically, if you want to analyze how the size of the conditional expectation, what you do, you take the derivative and study its trace, for example. That's the trace of a conditional covariance. And that conditional covariance, instead of scales with D, it's a D by D matrix. It scales the trace of the D by D matrix scales with K instead. So that's why, yes. Yeah. Okay, so so that's the intuition for why you should expect the iteration complexity to be K over epsilon instead of D over epsilon. Okay, so now let's move on to talk about another set of low dimensional structure, which is the Gaussian mixture model. I used the DALI 3 to generate this Gaussian mixture model in Van Gogh style. I think it does a pretty good job. Okay, so the Gaussian mixture model, I think many of us have worked on this. It serves as cornerstone for statistical modeling, and the study of it dates back to Pearson in 1894. And then after that, a vast body of literature has studied all different aspects of Gaussian mixture model. So basically, it's now a classic. It's a classic in statistics and machine learning theory. So here only have listed a very limited amount of papers on this. There is a huge literature on this. So the goal that we want to so the goal here is to study the performance of DDPM when your target distribution is actually generated from Gaussian mixture model. So you don't know that. You still run your DDPM and hope for the best. And it turns out that if your target distribution actually is generated from a Gaussian mixture model with covariance structure scales with identity, then it turns out that the output of DDPM sampler satisfies the following. Also have two terms. This is DDPM, so you don't have the Jacobian part. Okay, it has two parts. If you ignore the second part, you can see the iteration complexity is of order 1 over epsilon if you ignore log factors instead of d over epsilon in general. This means that although your Gaussian mixture model, the distribution is actually a full dimensional object, so there's no way that you can reduce it to a k-dimensional manifold, for example. However, the iteration complexity scales with 1 over epsilon. For us, this is actually a pretty surprising result. Okay, again, it's robust two-score estimation. And since we, okay, so this is a TV distance control. So the message here is that even in ultra high dimensions, it only takes diffusion models 1 over epsilon number of steps to converge compared to, in the general case, d over epsilon.
So can I ask a really stupid question? When I run these algorithms, you always stay in the space of Gaussian mixture models.
Right.
Right.
Yes.
So at least you're like in some finite dimensional space.
Right.
And
Exactly.
hope to have.
Exactly. For Gaussian mixture models, to run DDPM, you always in the process, in the forward process, it always stays in the Gaussian mixture models space. Yeah. So I guess that's why it actually works so well for Gaussian mixture models.
You expect this to only hold for Gaussian mixture of Gaussian models, right? Not a mixture of, for example, spherical models or anything else.
That's a great question. So at least we can generalize this result to approximate Gaussian mixtures. If you have a distribution that can be approximated well with these Gaussian mixture models, this also holds. You only requires like a 1 over epsilon number of iterations.
The error in approximating by mixture shows up in the upper bound.
Right. Yeah. So you will have an additional term that depends on the approximation error. Yes. Yeah. But we don't know whether it's more generalized beyond Gaussian. If you think about other mixtures, we don't know. Yeah. Sorry, what's the? Oh, the K is the number of mixtures. So we assume that there's K component. There's a K mixture. Yeah. Yes, the sample covariance matrix here in this result, we assume that it scales with identity. Yeah. But if you have a more general covariance, then this result will not depend only logarithmically in K and C. If you have a general covariance structure, this quantity will depend on the covariance structure.
So such a expression doesn't have sigma term.
Right, yes, because we simplified it to have to scale with identity.
What does the sigma scale?
Oh, in the general case, we're still working on it. So this is the ongoing work. So basically, this will scales with I think the minimum of K and D. K is the number of components. So if your number of components. No. This should, okay, in the worst case, I can only answer the worst case. If you have a general covariance, and then this should scale with the K, same K, and D, the minimum of K and D. Yeah. Yes.
So suppose I do have a general common covariance matrix among the components, and I stick in the updates, let's say like the sample covariance estimator.
Uh-huh.
It seems that I would be able to still retain this, would I not? To just keep track of everything. So you're updating with the identity here, but if I
Right.
updated it with the covariance information, you can estimate, would I still be able to retain this?
Well, so you can imagine the following. You estimate the covariance very accurately, then you scale your data so that you can return back to the identity design case. But that requires a very accurate estimator of your covariance.
To do the scaling.
Yes.
To do the, right.
Yes, to do the rescaling, yes.
Yes.
Yeah. But if you have enough samples, you can absolutely do that.
Just maybe one more stupid question, like, imagine that instead of so you're like, you break the symmetry if you have a general sigma because you transport to the isotropic Gaussian.
Right.
But like, what if I just transported to the Gaussian with the covariance sigma? Like, I could do that, like, I modify DDPM just with some sigma to the 1/2 and some strategic places. Like, do you think the answer is the same? Then you still just get the log squared KT. Like that's a version of Jason's question in the sense where like I estimate the sigma once and I change my algorithm to transport to the Gaussian.
Right. Yeah, so my understanding is that, okay, if you have enough sample, a lot of samples, so it asks for a very accurate estimate of sigma. So if you have enough samples, you are confident to do that and then plug in, then you will have that. Yes.
But if you have a good estimate of your score function, you already have a good idea of what sigma is also through that.
Well, so you see that in the score estimate, you actually have a it's very tolerant, right? You have the average across time, and then you have the score estimate bounded by some epsilon score. But if you want to do that trick, that's rescaling at first, then you probably need a very accurate estimate of it.
What you need in this condition, at least on the first time, and not the average.
But is it true that it's going to propagate in this like nefarious way? Is it true that you're going to have one term, which like an additive term in there, which is basically going to be the error that you have from that rescaling growth like okay?
So we haven't okay, so this is still ongoing work for the general covariance. So I don't have a definite answer for that. So my suspect is that you will have like a term that depends on the, yes.
The goal of this workshop was to not leave without a co-author, and I think it's still very potential.
Oh yeah.
Yeah.
So you might you have found a co-author.
Yeah, let's talk offline. Yes. Okay. So now this is a message. So compared to previous work, the previous paper studying exactly the same question, they provide a D over epsilon square complexity bound showing no adaptation to Gaussian mixture models. And there's other two papers. This is by Sitan Chen, also from Harvard and his group. And this is another paper where they focus on score estimation part using piecewise polynomial regression for estimated score. They combine this with existing DDPM convergence theory. So our work sort of serve as a complementary contribution because we focus our attention on the iteration complexity in terms of instead of the score estimation part. Okay, we still have a little bit time, so let me give you a very, very brief proof idea for just to give you some intuition. So the proof idea is that first you make the observation, as Boris already mentioned. For a Gaussian mixture model, you stay in the space of Gaussian mixture model. So basically, in the forward process, it always satisfy the Gaussian mixture model with the covariance identity and with different means and different mixture pi k, that different mixture component pi k. And the Jacobian matrix of your score function actually satisfy the following. So it can be written as the minus identity plus this which also depends on the mixture. I should use the mixture weights there. Okay, so now the key property that we establish is that through this process, along this forward process, the trace of this D by D matrix actually scales with log KT. So this is a D by D matrix. In general, it should scale with D. Or in the low dimensional structure case, the manifold case scales with K. So here we are able to establish the log factor scaling so that eventually your iteration complexity scales logarithmically in terms of KT without the dependence of D. Does that make sense?
So is that because this thing tensorizes? Like you're just doing a bunch of one-dimensional Gaussian mixture things and then you just kind of, they don't interact?
Well, so, okay, so what's the intuition? So only I know is that if you study this object for mixture weights that come from this Gaussian mixtures, then you can prove that this matrix actually degenerates in terms of it has approximately very low rank. But yes, but whether I don't know about the answer to your question, whether it's because, yeah. Yeah, that's the, yeah. Okay, so that's the proof idea. So just to conclude, in this talk, I talk about sharp convergence theory for diffusion models under mild assumptions compared to previously people often assume log concavity or smoothness for the score function. We're able to obtain those convergence results under very mild assumptions for a target distribution. And then I talked about how diffusion models automatically adapts to two types of low dimensional structures, one with low covering number, one with Gaussian mixture models. And here are our papers, and I want to thank my wonderful collaborators who show up in different papers. And with that, I conclude my talk. Thank you for your attention.